Okay, well, welcome to Chemistry 580, the University of Michigan. This is the winter term in 2021. And as we have been all year, we're going to be doing this class online, asynchronously, so the lectures will be posted on YouTube. We will have a one meeting time a week where we can discuss ideas, have interaction over Zoom, of course, and we can talk about starting the problem sets, which will be the main way that you interact back to me, I guess, in this semester. You can consult the syllabus yourself to see how it breaks down. There's no exams, thank goodness. There'll be a set of problem sets. They'll be pretty interactive, so that means they'll be doing things a little bit by hand, but a lot of it on the computer. The code I will provide will be in MATLAB. If you don't like MATLAB, then you can do it in a different programming language if you want to. You can convert the programs from MATLAB to something else. Sometimes that's a really good way to learn what the code really does. If you're more familiar with something else like Python, using one of the numerical interfaces for that, or whatever, Mathematica, it doesn't matter. I just find MATLAB to be really convenient, and as you know, with U of M, you can get MATLAB for free. So obviously that's not true for everybody. I will be making available all the code that you need for any of the assignments on the Canvas site. And for the people who might be outside of U of M, there will be at some point, but I can't make it the first priority right now, a repository of the code if anyone's interested in playing around with it. The lectures will be a lot on this board, so you'll be able to see, hopefully everything's lined up good. All right, so I write on the board, it shows up there, and I do some editing. I will invariably make mistakes, and I will fix those very, very kind of low-techly in my editing program. If I do something really bad, I guess I'll redo it. It's impossible to do everything perfectly, especially when you're like 6 inches away from your board. It's invariable that you'll make mistakes. There's a textbook for the course, which is the Ann Myers-Kelly book. It's a pretty practical textbook. It's not the most theoretical, but then the ones that are more theoretical don't have much practical stuff in them, and so it's a good balance. In my opinion, don't need it at all. You can consult whatever references you like. The course is going to be pretty self-contained, and we're going to start out with the basics. We're going to start out with the Schrodinger equation and derive things from there. So in some sense, we don't need any information from outside the course. There'll be a few mathematical identities that we need to employ that I probably won't bother proving. And I will try to absolutely give real-world examples of what we're doing. Those will be done, I don't know yet, we'll see, but I think it'll probably be done where I kind of present the lecture here, and then I maybe have some cutouts from the papers or whatever it is, data, showing real data. They'll just be able to put in the editing, or I might do it in a kind of presentation style where I give like a bunch of slides, and then you'll see me in a little box on the side. That might be more convenient. And if I'm doing things with animations, which we'll definitely do, because I love doing really simple models where things need to change, sometimes it's just easier for me to kind of play with those animations as I talk about what I'm doing. In a normal class, I would have just plugged my computer in and shown you the simulation or the calculation that I'm doing. Here, obviously, that's not as easy to do, but I can do my screen recording version of that. So that's probably how that's going to work when I want to play around with a model, two-level systems, or when we have laser fields, whatever. And then some of those demos become converted or sort of transferred into the problem sets when you have a chance to play around with them yourself. Equations are great, but I think that people, even theoretically minded people, do better when they have a chance to really manipulate the equations. And except for the most trivial examples, nothing really has analytical solutions. So we're 2021 now. We use computers, so you will learn how to do that one way or the other. There's a lot of spectroscopy courses at Michigan and other schools, and you might ask why. First of all, why do I want to take a spectroscopy course? I'll get to that in a minute. The second is, which one should I take? right? There's so many. Why are there so many? The organic chemists have one, the analytical chemists have one, physical chemists have one. I'm sure other departments have them too. And the simple reason is because spectroscopy means different things to different people. If you're interested in figuring out how to measure a property, or if you are going to a lab and you're going to use some sort of gadget, some apparatus, then you might want to know the details of that apparatus. You know, what does this button do? What does this piece of the componentry do? What does this diffraction grating do? What does this slit do? All right, how do I shim a magnetic field in an NMR? This is not a course about that. That's in my opinion, that's really like learning how to use the user manual of whatever it is gadget that you have. Most commercial instruments come with user manuals which tell you everything you need to know, even including some of the theory, believe it or not. So this is not a course on user manuals for spectrometers. This is a course on understanding the very deep connection between spectroscopy and chemical structure and dynamics. Right? That's what this is about. So although it's true people use spectroscopy as a tool, for example, to find out how much stuff they have, this is not what we care about in this class. You know, do you think the absorption gets more when you have more stuff? Yeah, it does. Okay, that's it. That's all. That's more or less where that ends. We're not going to get into penetration depths or, you know, even Beer's law. You can. That's a very, very simple, you know, exponential decay. You don't need to take a graduate course on that. What we're interested in is, you know, what are the energy levels of a molecule? What does that mean? What does it mean that there are energy levels of a molecule? How do you know what they are? And if spectroscopy is a tool for figuring out what the energy levels of the molecule are, let me show you a puzzle right now. Pick any quantum system you know, all right, where there's something bound. It needs to be bound. Let's say, I don't really care which one it is. You might like the hydrogen atom, right? So how do I represent the hydrogen atom? One way to do it is to plot the potential energy function for an electron bound into a hydrogen atom. Well, it's a Coulomb interaction. It looks like that, right? This is the distance between the electron and the nucleus, and this is the potential. It's 1 over r with a minus sign because it's attractive. And we know you can solve the hydrogen atom problem analytically. It's extremely hard if you've ever tried to do it. I did it once in a course, and I'm never going to do it again. There it is. The 1s orbital is the lowest energy. Then you have the 2s and the 2p because they have the same energy. For a proper hydrogen atom, they split when you have something with more than one electron. And then you have the 3s and the 3p and the 3, whatever, you have the n equals 3 level, right? Okay, so that's a proper quantum mechanical system. You might have a harmonic oscillator. We know harmonic oscillator energy levels are equally spaced like this. There's a minimum energy that's not the zero, which we call the 0-point energy. Here's the potential energy for a harmonic oscillator. Let's say the coordinate there might be called x, the displacement from equilibrium of your mass, right? So this would be x, right? Of course, we model molecular vibrations this way. We model electronic structure this way. Maybe you don't like that. Maybe you like a particle in the box, okay? Particle in the box, there's a potential. It's 0 inside, between 0 and, let's say, a, some distance, in which this confinement is taking place, and you have the ground state of the particle in the box, and you have the first excited state, and you have the second excited state, and they're actually spaced quadratically, right? So n equals 1, n equals 2, n equals 3. Okay, and so these are some reasonably good quantum mechanical systems that you can solve analytically. You can write down a formula that tells you what the energy levels are and what the wave functions are. So there's nothing essentially unknown about this. Obviously, there are not too many. This is one of the limiting. This is about it. The list is not very long. So what do? Well, one of the things that we do is we imagine that our more complicated system is kind of similar to these. One of them, for example. So maybe I have a harmonic oscillator. Maybe instead of a harmonic oscillator, I have an oscillator that's a little bit inharmonic. Right. So the real potential of energy function is not a parabola. It's something else. Maybe this. That. Right? So it curves over a little bit. What do you do about that? Well, some of them, one particular one, like a Morse oscillator, you can solve exactly. But a lot of times you can't, so you represent your real problem in a basis of the harmonic oscillator. And then you solve the Schrodinger equation, or you diagonalize a Hamiltonian, and you get energy levels from that. All right, so the point is, a lot of times in chemistry, especially, we take reference problems that are exact or that we completely understand, and we try to tweak them a little tiny bit and then have our real interesting system be similar to those, right? So, but that gives us some energy levels out. Sometimes we need to use approximations. What if we have 2 electrons in a hydrogen atom? Well, 2 electrons in a hydrogen atom would be like H minus, or if I have helium, which has automatically 2 electrons in it, then we have a problem because the 2 electrons interact with each other as well as with the nucleus, so that we cannot solve that problem. I cannot write it down analytically. You can solve it numerically to as high a precision as you have the patience for, but you can't write it down analytically. So when we have more and more and more electrons, we start to actually not solve the problem exactly. Right? Even 7 or 8 electrons starts to push our current theories or current methods to their limits of exact, whatever that exact means, numerically exact. So we make approximations. Well, now we've started to add in a new wrinkle here. It's one thing to use a known problem as a basis for an unknown problem, but you can still solve it exactly as long as your basis is good enough. Here, when you have 2 electrons, well, you're making physical model. A physical model means that the thing you get out is only going to be as good as a physical model can be. So if you use Hartree-Fock and you think about electron-electron repulsion as a field interacting with another electron, well, you're not keeping all of the information that we know about what electrons really do. It's not perfect. And so you can only ever do as well as you can do with that theory. All right? So when you start to realize, when you do things that give you energy levels, theoretically, let's say, you may often have to rely on some sort of model that tells you what's going on. If I take an electron and excite it to excited state, well, the problem I had that was already hard in the ground state, because I have more than 1 electron usually, unless it's a hydrogen atom, it's going to change again because now an electron has been moved. Its structure has changed. It's in a different spatial orbital. So the way it interacts with the other electrons is also going to change. So you don't just get for free all the excited states of an electronic system by just knowing all the unoccupied states. That doesn't work. You have to actually do more work to figure out what happens when an electron is excited. All right, so what that means is, what states are we even talking about? What are the states of a molecule? And that's not so clear. We still don't really know a simple automatic way of figuring out all that stuff, especially when you include electronic excited states. All right, vibrations, perhaps you could argue it's more understood. Although if you go and do a quantum chemistry calculation of the vibrations of a molecule, you're going to get the harmonic frequencies. You're not going to get this curvature here, right? You can do an anharmonic calculation, and you're going to see there's a reason why everyone does not do anharmonic calculations on every molecule, because it takes much longer, all right? And even then, it's using usually some approximation method like vibrational perturbation theory, right? You're not literally doing the entire Born-Oppenheimer surface, expressing it in a basis and diagonalizing the Hamiltonian. That's very rare. I mean, that's a research topic. That's not a package that you do with Gaussian. All right, so the point is that we often do not know about excited states, all right? Certainly above the lowest energy ones in a vibration or highly excited electronic states of a molecule. And as the bigger the molecule gets, the less we're going to understand about the electronic excited states. So what spectroscopy is supposed to tell us, in the analytical chemistry view of things, you have a beam of light, and of course there's more kinds of spectroscopy than this, and you have a sample. There we go. All right. Believe it or not, I am an experimentalist, but I like to abstract things as much as possible. All right, so there you are, beam of a light and a sample, and then what happens, of course, is the beam of light comes out, and it's a little bit dimmer, right? That's sort of the one way of thinking about this. And the amount dimmer that it is at different wavelengths tells you what was absorbed. And then that could, in principle, tell you, maybe, about energy levels in that molecule, in that sample, and the differences between them. It doesn't tell you their absolute energy values. You need to know something like maybe the ionization energy, if you want to know the absolute energy relative to some other, let's say arbitrary energy scale. That's interesting, especially for electrochemistry. A lot of times we just know about energy gaps, but then we make a model and then that can tell us something else that we might want to know. Okay, so if we just need to know how much energy was lost and at what frequency, which is sort of like what traditional analytical chemistry style things are about, then that should tell you, okay, so you look in the spectrum, you see, I see, here's my absorbance, which I have to convert transmission to absorbance. But like I said, this is not a class about Beer's law. So there's a way to do that. And you get a peak, right? And it's at some frequency, which I'll call omega naught. When you do a real experiment, you do not usually see a straight line, right? Even if you do NMR, which has about some of the narrowest spectral lines you'll ever see, it has some spectral width. Now, what you could probably do is get a better NMR spectrometer, and then you would find out there's even more lines, because those lines would be not resolved in a traditional organic chemistry style 300, 400, 500 megahertz machine. But if you took the same NMR spectrum of your small organic molecule and brought it to the a gigahertz NMR spectrometer, you would see lots and lots and lots of spectral lines. All right, you might also see that even then you'd have some spectral width. All right, what other things have very narrow widths? Rotational bands also can have very narrow widths. All right, and that can be measured by higher and higher resolution spectrometers. But even if you go to the highest resolution, you will still see there's a width, and the widths come from all kinds of different phenomena, which we're going to spend a lot of time talking about that, because a lot of times the frequency of this is not interesting. You want a carbon-hydrogen stretch, it's going to be around 2,900 wave numbers, give or take. Fine. So then if you want to know how much CH stretch you have, just look at the amplitude and you're done. But if you want to know the environment of the CH stretch, maybe it would shift a little bit from frequency to frequency, but maybe the width is going to tell you much more. The width tells you about interactions with the environment. It also tells you about distributions. How many different kinds of CH stretch environments do you have? I don't mean this in the way that you might have learned about NMR spectroscopy with like different kinds of protons or different kinds of carbons and how they couple differently or otherwise. I mean like a hydrogen, for example, in a water molecule with a short hydrogen bond versus one with a long hydrogen bond. This is probably going to be one of the toy models that we come back to over and over again, because it's such a perfect example of a phenomenon that's ubiquitous in spectroscopy, which is called inhomogeneous broadening. Of course, the frequency will be different for the OH stretch, which is going to be, for the one that we're interested in now, this hydrogen bonded one. It turns out that when the oxygen-oxygen distance is very short, the OH stretch frequency is low. And when the distance is large, the frequency is high. And the highest it can be is when it's in the gas phase, which means when it's basically infinitely far away from another water molecule. Understanding the OH stretch spectrum has been one of the challenges and, in fact, one of the triumphs of modern nonlinear infrared spectroscopy. That's my field, so I'm very happy that my colleagues, I didn't do any of this work, but my colleagues did, and it's a perfect example of how to use new tools to understand old problems. All right, so you got your peak, you realize that there's some width to it. One of the reasons why there might be a width is because there's different environments. Another reason is because there's very fast collisions with the solvent, or whatever the environment is. Another possible reason is because when that molecule is excited, it has a finite time it stays in the excited state. Now in chemistry, that's almost never the reason why you have the width. In gas phase atomic physics, that happens and becomes an important broadening mechanism. But in condensed phase chemistry, it's almost never important. And so the main sources of broadening in chemistry are this, inhomogeneous broadening, and very fast collisions with the environment. Now, I say that as if, where do I get that from? Well, it turns out we get that from a lot of experiments. But in this course, we're going to be able to derive an equation that starts, on 1 week at basically the Schrodinger equation and ends with a formula that tells us how to predict the line shape function based on the dynamics of the molecules in the solution, or the molecules that they're in their environment, some sort of environment. So we need to build a lot of machinery to get that. We need to understand, how does light interact with molecules? We need to understand, how do molecules interact with their environments? And we need to basically be able to understand, how do we describe spectroscopy? All right, here's my first conundrum number one. That seems obvious, but it isn't really. So the yarn, that means the old story everyone tells, is that spectroscopy is supposed to be about energy level differences. Well, what are energy level differences from? They come from having a Hamiltonian. Now the Hamiltonian, presumably, even if you're, so let's pretend you're the best quantum mechanic there is, and you can solve this. Right? Maybe it turns out that the energy levels are quantized for most of the cases of chemistry that we're interested, they will be. All right, because there's some binding, right? Binding causes anything confined will have quantization. All right, there's some energy levels and there's some eigenfunctions, if you like to think of things in terms of space, which chemists often do, unless they do NMR. No one ever writes the wave function down for spins. Okay, so we're gonna be very comfortable talking about these as vectors in Hilbert space, which is the correct quantum mechanical way to think about things. And nevertheless, there's these different eigenfunctions or eigenvectors associated with a particular eigenvalue. And because there's more than one usually, then there'll be some distribution or some ladder of these. And our spectroscopy ostensibly is supposed to tell us about the energy differences. That's what we said, right? That's the thing you start out with. I showed you a bunch of systems up here. Okay, so then let's start thinking about what the actual experiment would look like. It would look like having a sample, and the sample is going to be the stuff in there. And I'm not going to worry about how thick it is. So for all we care, this could be one molecule. Right? We absolutely now know you can do spectroscopy on single molecules. The Nobel Prizes have been awarded. You can buy apparatuses that will do this. So here's what we'll do. We'll put a little knot here to remind ourselves that this is the Hamiltonian for the molecules. And I'll put a little knot up here. And we'll see this notation come back many times. All right, so that we have a Hamiltonian that describes the molecular system. How do we see it? We can't just write this down. We need a way to make measurements. Okay, so you fire up your laser. Okay, so now we have a laser. Well, what is a laser going to do? The laser has to do some interaction too. So let's call that H primed. Okay, so you see what the issue is now. The Hamiltonian that we started out with is only part of the problem. It's this part of the problem. To interact with it, we need to add a laser, which I'll call H prime. Okay, so now, without even solving the problem, what do you know? Well, you know that when the laser is on, these aren't the eigenvalues. These aren't the eigenvectors. This problem is not the problem when the laser's on. It's a different one. Well, that's weird. Your laser is going to change the energy levels. There's no way around it. You can't take this out. The laser will change the energy levels. So what does that mean then? The laser is basically changing the system. Right, how do we deal with that? That seems very strange. Well, we have two ways to go forward, right? One way is we keep the laser, or the electric field, completely intact. And we treat it just like another term in the Hamiltonian, and then we solve somehow the Schrodinger equation for this system. You know, obviously the laser will probably depend on time. So that means that the system will not have a single set of eigenstates. It's going to be evolving as you change the laser on and off. But you can do it exact. And then you might ask yourself, okay, what's our Gedanken experiment? This will be our Gedanken experiment for a lot of this course. We have our laser and we turn it on and we turn it off. I don't mean this to be a pulse. Of course, it could be a pulse. That's what my lab does. But you just imagine you have your laser on, your helium neon laser, or even just the lights here that are lighting me up. You turn them up and then you turn them down, right? Turning on and turning off. This is time. And for simplicity, let's just call this the intensity. We're going to be thinking a lot about the difference between field and intensity, which turns out to be especially important for nonlinear spectroscopy. Okay, so you can treat it exactly. All that means is that the quantum mechanical system changes as you do the experiment. But, as you'll see, what you can do is you can ask the question, what's the probability, given I start in one state system of the system, so I forgot to put little O's here, zeros. So what's the probability I start out in state n, whatever it is, at time 0, and I end up in some other state, state m, at time t. Okay, that's going to be a thing that we calculate a lot. All right, it's going to depend on the nature of our interaction, for sure. It's going to depend on, how strong the field is, what the frequency of it is, right? So if you already know the answer, which is going to be that the frequency of this should somehow be pretty close to matching the frequencies of this, right? But what about this issue? So the issue, of course, is that when the field is on, the whole composite quantum system is not the system that it was when the field is off. So it's mixed together. We have a hybrid literally hybrid light matter coupled system. So part of the wave function is the light, and part of the wave function is the molecule. This is not science fiction. This is the way it works. But we're not really interested in the state of the system with the light on most of the time, right? We're interested in knowing what are the states of the system without the light on. And if it so happens that because of our ineptitude as experimentalists, the only thing we can do is interact light with this thing, then we're going to wait. We're going to wait till our disrupting field is gone and ask the question, okay, what's the probability that we made the transition from state n to m at time t, where t is like, let's say, quite a bit long after the pulses or the field is gone? Well, then, the system will probably, be in some state of it will definitely be in some state of the field free. So let's call that phi m. It started out in phi n over here. Okay, with the zeros, right? And then this is the thing that we want to understand. What's this transition probability? That's basically what we're asking. Mathematically, it's actually very straightforward. It is simply this so-called scalar product. Right? This is the probability that we go from n to m. All right, so we're going to work out how to calculate this probability. All right, now there's going to be a few issues. This turns out to be not very practical. It's not very practical to calculate the whole Hamiltonian of the whole system exactly as the light goes on, comes off, and then we see what happens. That's not very practical. Right? What's much more practical is to treat this approximately. All right, so what we're going to do is we're going to treat this whole thing, but we're going to assume that this interaction is weak. Okay, now if the interaction is weak, we can use something called perturbation theory. And when we develop time-dependent perturbation theory from scratch, if you want to look it up in a textbook, you can, but I'm going to start from the Schrodinger equation or from the so-called Liouville equation, which is the time-dependent equation of motion for the density operator. We're going to derive perturbation theory from scratch, okay? And then we're going to use it, and we're going to derive the response function. So we see how does interacting light with the material work. Now you might ask, well, how do I know which to do? Can I always use perturbation theory, or should I do it exactly? All right, well, there's fortunately a two-level system comes to our rescue. All right, so we're going to do a lot with two-level systems. A two-level system has two levels, obviously, and then we can couple them together to make them a little bit more interesting. We can couple them with a field. The field might be constant, the field might be oscillatory, the field might have complicated frequency time dependence with a shaped laser pulse, and then one of our problem sets looks at that. Fortunately, in 2021, solving this numerically is trivial. It's a few lines in MATLAB, and you can solve the Schrodinger equation with whatever field you want. That's wonderful. Now, that might have been true in the past, but it's fast, so you can do thousands and thousands of iterations if you want. So what we're going to do is we're going to use the fact that with a two-level system with a field, we can calculate it exactly. And with a two-level system with a field, we can also calculate it using perturbation theory. And we can directly compare them. And we can come up with some rules. We can say, yes, I see. When the field does this, and I see this characteristic thing, I know that my perturbation theory result deviates significantly from my exact one. And that will give me some bounds on when I can use the perturbation, because this weak thing here is hard to know. It's hard to know whether it's really weak or not, and whether it's appropriate or not. Okay, so the sort of program that we have for us is a review of basic quantum mechanics, because I know that some people will have different backgrounds. And thanks to taking that quiz, I'll be able to maybe guide the level a little bit better, or hopefully a little bit better. We'll develop the basic time dependence of quantum mechanics when you don't have a time-dependent Hamiltonian. So when this whole Hamiltonian is constant, it turns out to be relatively simple in that case. But then we're going to throw in the fact that, of course, if you do an experiment of spectroscopy, you're going to expect to have a time-varying field. Time-varying fields can either be done exactly or with perturbation theory, right? So then we'll work that out. We will develop the so-called time-ordered exponential operator that will let us do perturbation theory. And then we'll learn a few very important results. We'll learn about Rabi oscillations. We'll learn about Fermi's golden rule, though that might come a little bit after that. No, we'll do look at Fermi's golden rule, when one of the most important relaxation understandings of relaxation in modern chemistry. And then we'll basically use this as a stepping stone to develop optical response functions, which will lead us to nonlinear optical response functions, and that will allow us to understand with one framework all of optical spectroscopy from your linear spectroscopy like FTIR or UV-Vis spectroscopy, all the way to more modern, and NMR, of course, and all the way out to second harmonic generation, some frequency generation spectroscopy, pump probe, fluorescence, time resolved fluorescence, and of course, multidimensional spectroscopy, which is the field that I've been involved with my entire life, basically my entire science life. And in fact, the field has basically existed as long as my science life had. So we've grown up together. I will use many examples from the current literature, some from my group, some from other groups, to try to pinpoint attention onto key cases where you see directly this remarkable connection between a measurement of spectroscopy and a behavior of a chemical system, right? Because it's not really enough to understand, to get what these energy level differences are. That's not really what we want to know. That you can actually learn in about 2 or 3 weeks. And then the rest of it's owner's manuals for the gadgets, right? What we want to get to is to really have an intimate and deep relationship. What's actually happening in the molecule when you shine light on it? What really happens? What's the physical event? And then that actually is great. It lets you understand very quickly how spectroscopy arises as an interference between an emitted signal field and the transmitted probe field, which is your excitation light. So we'll think about interference. We will almost never discuss the word photon, because it turns out that, except in very rare cases, you don't need to use that terminology. Most experiments that we do are classical. You have an electric field, and you can think of the electric field classically. Now, of course, there are examples, some of them quite current examples, where some quantum nature of the optical field is used or exploited or taken advantage of to do spectroscopy. And I will briefly discuss that a little bit, particularly because the Goodson group has been working very hard on that. But they're one of the only ones who are working very hard on it. So despite its ubiquity in quantum computation and information processing and quantum optics, most experiments that you do in the lab are done with classical light fields, or can be described as using classical light fields. And so we will mostly focus on that. And just so you understand how this works, the videos are going to be on the order of 15 minutes or so. I will probably edit them by cutting them off. I will be honest, I did this in a previous class that I taught last semester, but it was on material that I was not anywhere near as conversant with. I can probably teach this class without looking at my notes, which is a bad thing sometimes because it means I can just go on and on. So I am going to focus very hard on condensing the information and being as efficient as I can with these lectures to save you time, but also to make it much more manageable in terms of the time that you spend on the various topics. So I'm going to force myself to make them self-contained, like roughly 15-minute sections. Some will be a little bit shorter, some will be a bit longer. Typically when I'm doing anything with a demo or interaction stuff, that can drag on a bit more, okay? And so yes, the next bit, we're going to start right into the review of quantum mechanics, which will be based on the postulates, and then we'll go there bit by bit, working on chipping away at developing the formalism of time-dependent quantum mechanics perturbation theory, and then that will get us to talking about both the time evolution of the wave function and the time evolution of the density matrix. The density matrix is very important because it allows us to handle thermal effects or temperature effects, and that's very important. Almost nobody does experiments at 0 Kelvin, and wave functions are only useful at 0 Kelvin. So we want to be able to include effects of baths and systems, and we're going to develop red field theory, and that's going to be super important for getting us to be able to see how to connect the dynamics and the spectroscopy. All right. And yes, we'll definitely discuss infrared and electronic spectroscopy and some of the things that you might want to know about those things that are beyond just how much stuff do I have in my sample, things about symmetry and selection rules, but mostly by way of examples. Because those are, when you do this for real, like in your research, you will go and you will learn about the molecule you're studying. And if I tried to describe every single conceivable thing, it would be an extraordinarily overwhelming amount of information and not very interesting to most people. So I will show a few examples, and then I will try to pick the ones that are the most general. And that's one of my advantages of being older. Not that I'm smarter, but I have more experience in knowing what are the unifying concepts. When I say something is general, as opposed to like how a mathematician would say something is general, I mean, is it generally practically useful to know this thing, right? Is it generally practically useful to understand this physical idea? Not is it general, does it apply to all Hilbert spaces? I don't mean that kind of thing. I mean, if you learn about two coupled vibrations, are you going to be able to use that information to understand anything else? Well, it turns out you will. So I'm going to try to focus on the things that are similar rather than the things that are different. I think it's actually quite easy to find differences. Finding similarities, both in science and in society, are probably more valuable to us as moving forward and being creative. And so that's going to be one of my goals, to show you how I was able to make connections. It took me a very long time. And so one of the advantages, you don't have to spend 20 some odd years to figure out how to make those connections. All right, I'm really looking forward to this course. And I think it'll be interesting. I've done it once before. And yeah, so welcome to the class.